Welcome back to another video. Now, let's dive in on inference on the difference in means of two normal distributions when their variances are known. We have two populations, and instead of studying them individually, we want to better study them relatively. We want to see how far their means are. Suppose we have a random sample of size n, x1, x2, up to xn, with an unknown population mean, mu of x, and known variance sigma squared of x, and a second independent random sample of size m, y1, y2, up to ym, with an unknown population mean, mu of y, and known variance sigma squared of y. We are interested to make an inference on the means of these two populations. Everything we discussed are summarized here. We have two independent populations represented by x and y. We have two independent random samples, one from each of these populations. And we are assuming the variances of these populations are known. We can assume that a sample mean is a very good, even the best, point estimator for population mean. The difference in sample means, x bar minus y bar, would be our best point estimator for the difference in population means, mu of x minus mu of y. We can easily use the linear properties of expectation and variance to calculate the expectation and variance of this point estimator, and use it to build a new standard normal statistic, which can help us construct the confidence interval around the difference in population means. The new normal statistic is x bar minus y bar minus mu of x minus mu of y, divided by square root of sigma square of x over north plus sigma square of y over m. Here, we are hypothesizing on the difference in population means when the population variances are known. As a result, we are using a z-test or a normal test for these three cases. To find the value of the z-test, we need to plug in the values of sample means for both samples, x bar and y bar, sample sizes n and m, the hypothesized value on mean difference, delta 0, and known population standard deviations, sigma x and sigma y. In case A, a two-tailed test, we are testing for deviations in both directions from the hypothesized difference. This means that we are interested in whether mean population difference is either greater than or less than the hypothesized value. For example, I want to determine whether there is a significant difference of delta 0 in the average test scores of students who took version A versus those who took version B of the exam. The null hypothesis would state that the mean difference is equal to delta underscore 0, while the alternative hypothesis would suggest that the mean difference is not delta underscore 0. To calculate the p-value for this test, we first find the value of the z-test statistic, and then we calculate the probability of observing a z-test statistic as extreme as the one we found, in either direction. This is the highlighted area in part A bottom figure. This gives us the p-value, which helps us decide whether to reject the null hypothesis. If the p-value is very small, it suggests that the observed result is highly unlikely to happen by chance, so we reject the null hypothesis. The rejection region for a two-tailed test consists of both the upper tail and the lower tail of the normal distribution. If the test statistic falls within either of these regions, we reject the null hypothesis. These areas are determined by the chosen significance level. If we set alpha at 5%, the rejection region is split equally, with 2.5% in each tail, from negative infinity to negative z-value of 1 minus half alpha and z-value of 1 minus half alpha to positive infinity. We will reject the null hypothesis if z-test statistics falls in this rejection region. The upper-tailed test, case B, is used when we are specifically testing whether the difference in population means is greater than the hypothesized value as stated in the alternative hypotheses. In this test, the p-value is calculated by finding the probability of observing a z-test statistic greater than the one we calculated. If this p-value is small, it indicates that the observed value is unlikely to occur under the null hypothesis, leading us to reject the null hypothesis in favor of the alternative. In this test, the rejection region is in the upper tail, meaning we only consider whether the z-test statistic is significantly large. If the test statistic falls within this upper rejection region, we reject the null hypothesis in favor of the alternative. The size of this rejection region is determined by the significance level, such as 5%. The lower tail test, case C, is used when we are specifically testing whether the population mean is smaller than the hypothesized value as stated in the alternative hypotheses. In this case, The p-value is calculated by finding the probability of observing a z-test statistic smaller than the one we calculated. A small p-value suggests that the observed result is highly unlikely to occur under the null hypothesis, leading to a rejection of the null hypothesis. In this test, the rejection region is in the lower tail, meaning we only consider whether the z-test statistic is significantly small. If the test statistic falls within this lower rejection region, we reject the null hypothesis in favor of the alternative. Again, the size of the rejection region is determined by the chosen significance level. Let's go over an example together. A car manufacturer wants to compare the average fuel efficiency, miles per gallon, of two different car models, Model A and Model B. A random sample of 40 Model A cars gives an average fuel efficiency of 30.2 mpg, while a random sample of 50 Model B cars gives an average fuel efficiency of 28.5 mpg. The population standard deviations are 3 mpg and 2.5 mpg for Model A and Model B cars, respectively. The company wants to test if Model A has a significantly higher mpg than Model B at a 5% significance level. Please pause the video here and try to perform a hypothesis test and tell the manufacturer if Model A has a significantly higher mpg than Model B at a 5% significance level. First, we can see that we have two samples representing models A and B. We can also see that we are interested to study the difference in population means to see whether Model A is better than Model B. Finally, we can see that the population standard deviations are given, which means that we should use a z-test for two samples. We can see that the claim of interest is to see if the mean mile per gallon of Model A is better than that of Model B. If we represent Model A as x and Model B as y, the alternative hypothesis is μx is greater than μy or μx minus μy is greater than 0. As a result, the null hypothesis should be μx minus μy is less than or equal to 0. By plugging in values of sample means, sample sizes, population standard deviation, and the hypothesized difference, we can report the value of our test statistic is 2.87. Next, we need to find the p-value, or the rejection region, to make a conclusion. Given the fact that we are running a upper-tailed test, the p-value is 1 minus the CDF of our z-test value, which is 0.00203. Given that p-value is less than alpha of 0.05, we can reject the null hypothesis. As for rejection region, the rejection region of an upper-tailed test is z-value of 1 minus alpha to infinity, which is 1.645 to infinity. Given that z-test value falls within the rejection region, we reject the null hypotheses. In both approach, we reject the null hypothesis and report Model A has a significantly higher mpg than Model B at a significance level of 0.05. Let's go over an example in Python. We want to compare the height of two European countries at 1%. The first group consists of individuals of Italian nationality. The variance of the Italian population is 5. The second group is taken from individuals of German nationality. The variance of German population variance is 8.5. We want to know if Italians are taller than Germans? First, we can see that we have two samples representing Italian and German nationalities. We can also see that we are interested to study the difference in population means of Italians and Germans. Finally, we can see that the population standard deviations are given, which means that we should use a z-test for two samples. We can see that the claim of interest is to see if Italians are taller than Germans. As a result, the null hypotheses should be mu Italian minus mu German is less than or equal to 0, and the alternative hypotheses should be mu Italian minus mu German is greater than 0. We need to load the ztest2 function and pass necessary arguments, such as the sample data, the hypothesized difference, population variances, and the alternative is less. The function returns the responding z-value and p-value along with a two-sided confidence interval. If interested in using the rejection region approach, please use Python to directly retrieve critical z-values and define the rejection region. You can see that the formulas for the type 2 error and the sample size here. The approach to derive these formulas are similar to what we discussed for a single sample z-test. Thank you for watching this video.
See you in the next one.